finding rotational inertia can be as simple as looking up an object in a table like this that you find in most textbooks. So we would look for the object of interest. Maybe it's a rod. And our axis of rotation, if the axis of rotation passes through the center of the rod, it rotates like this. We could look that up here and we could see that the rotational inertia is 1/12 times the mass of our rod times the length squared, 1/12 ml squared. And if the rod is rotating about an axis that passes through its endpoint, like this, or let me rotate this 90 degrees so the axis of rotation is pointing toward the camera. Now we look this up, and it's also on this sheet. It's 1/3 ml squared. What if the axis of rotation is not at the end of the rod or at the center of the rod? Maybe it's here. Maybe the axis of rotation isn't even passed through the rod. Maybe it's over here and the rod sweeps out sort of a washer shape, a donut shape as it goes around. Well, then this chart isn't very helpful, is it? But using this chart in conjunction with the parallel axis theorem opens up a whole world of possibilities and gives us a lot of different options for finding rotational inertia. The parallel axis theorem says that if we know the rotational inertia for an axis that goes through the center of mass of our object, then we can find the rotational inertia for any other axis of rotation that's parallel to that one. So if I have a rod rotating about an axis of rotation through its center point like this, through its center of mass, and I know that that's 1/12 ml squared, I can find the rotational inertia of an axis that goes through this point, or an axis that goes through this point, or an axis over here. Any axis that's parallel to the one that went through the center of mass. This equation starts with the rotational inertia about an axis that passes through the center of mass of our object, I center of mass. And we add to that the mass of our object multiplied by the square of the distance between the two axes of rotation. The distance between the center of mass axis and the parallel axis of rotation, the one that we are interested in. So I is the rotational inertia about an axis of rotation that does not pass through the center of mass, some parallel axis. That's typically the one of interest. We want to know the rotational inertia about some axis of rotation that does not pass through the center of mass. What do? We say, is there an axis of rotation parallel to it that passes through the center of mass? And we look that up, see if we can determine that fairly easily. And we add to that the mass of our object times the distance between these two axes of rotation squared. And that gives us the rotational inertia that we want, the one about the parallel axis. So here's a rod, and we already integrated over our rod, and we found that when it rotates about an axis of rotation that passes through the center of mass, we got 1/12 ml squared. M is the total mass of the rod, L is the total length. We also integrated and found that if the axis of rotation goes through the end of the rod, we got 1/3 ml squared. We know the result. Let's see if we can get that using our parallel axis theorem. So I here is the red axis of rotation, the one that passes through the end of the rod. That's going to be equal to I center of mass plus M d squared. So we look and see we've got a rod, we've got an axis of rotation that passes through the end of the rod. And we say, is there an axis parallel to this one that goes through the center of mass? Yes, there is, and we know that's 1/12 ml squared for that rotational inertia. And what is this d? The d is the distance between the axis that goes through the center of mass and the one that we're interested in. In this case, it's this distance right here, which is L over 2. So we get the same thing we got when we integrated over the rod. That's good. We can use parallel axis theorem to get the rotational inertia about an axis of rotation that passes through the end of the rod, or we could just integrate over our object and find it that way. Let's do another example. Let's take a rectangular piece like this. We want to know the rotational inertia about an axis of rotation that passes through a corner of our rectangular object. So here's my piece. I'm going to make it a square to make the math a little easier to see. We have a square flat object that's rotating about one corner. And we know that the rotational inertia is going to be the rotational inertia for an axis parallel to this one that passes through the center of mass plus md squared. But we want to know, is there an axis parallel to this one that goes through the center of mass that we can look up? And this is what I found in the table. A rectangular flat object rotating about its center point. So that's an axis of rotation that passes through the center of the object. I'll use a blue pen since they drew that in blue. I'll use a blue pen. It goes right through the center of our object, perpendicular to the page. And I can start filling in some numbers here. This is going to be 1/12, the mass of our object, times, let's just call this L, and it's square. So it's going to be L squared plus L squared, and that's the I center of mass. And we're going to add to that the mass of our object times d squared, and d is going to be this distance between the two axes of rotation. And d is L over 2 times the square root of 2. And we're squaring that. So I have 1/6 ml squared plus 1/2 ml squared is 2/3 ml squared. I hope you're seeing the utility of the parallel axis theorem. If we look at this table, there are very few situations that this table is actually going to help us for. The rod rotating about an axis of rotation through the center of the rod or through the end of the rod. Those are here. But any other location is not in this table. The flat rectangular object rotating through its center point is here, but not any other location. But with the parallel axis theorem, we can take this table and find a lot of other configurations that are quite useful.